Mercedes-Benz Stadium was not merely a new construction, it was a necessary solution to overcome the limitations of the existing Georgia Dome. Completed in 1992, the Georgia Dome was once considered innovative with its air-supported roof, but over time three major issues emerged. First, high maintenance cost and roof instability due to climate sensitivity. Second, lack of spatial flexibility to accommodate diverse events. Third, limited competitiveness in meeting demands for premium seating and multifunctional use. As a result, the city opted not for renovation but for a completely new stadium with a reimagined structure and concept. At the heart of the project was the fundamental question: what kind of roof should we choose?
We started at the roof and we said, how could this roof do something that was...
We'd sit down together in a conference room with drawings and tracing paper and pens, and we'd sketch things up.
The proposed options include a sliding roof, a cell-structured roof, and HOK's rotating 8-panel roof. The cell-type roof was costly and complex due to its curved panel geometry. The sliding roof had technical risks and slow opening-closing speeds. Ultimately, the chosen solution was the world's first retractable roof, consisting of 8 triangle panels that rotate toward the center to close. Interestingly, in the case of Mercedes-Benz Stadium, the roof structure was determined first, compelling the entire architecture design to progress top-down. The primary structural challenge was how to efficiently distribute these complex and unbalanced loads throughout the building. To resolve this, an octagonal fixed truss was established to evenly distribute the roof's weights and motion horizontally, supported by 8 strategically positioned mega columns. The loads transmitted through these mega columns are vertically transferred deep into the ground via a composite foundation system of mat foundation and drilled piers. In summary, Mercedes-Benz Stadium's structure follows a load path that begins at the roof, dispersed horizontally through trusses, and descends vertically via megacolumns and foundations, an engineering system organically designed from the top to the bottom based on roof behavior. However, unlike design, construction always progresses from the bottom to the top. Hence, in this video, we will explain the progress in reverse from the foundation to the roof. Along the way, we will highlight each structure element's design intent, construction challenges, and corresponding solutions. Now we will examine these elements in the order of the actual construction process. First, we will talk about the foundation, which transfers the load of the stadium to the grounds, and the mega columns, which support the trusses above it. The stadium must support tens of thousands of tons, including 3,700-ton roof trusses, 500-ton panels, 19 mega columns, and interior loads. These highly concentrated loads required a precise pre-construction load distribution strategy. A pile raft foundation, a combination of a mat foundation and drilled piers, was adopted. The mat foundation consists of a thick concrete slab under each column with an area of about 100 square meter, capable of supporting roughly 3,300 tons per set of 3 columns. However, due to weak shallow soil and large dynamic loads, the mat foundation alone was insufficient. Therefore, drilled piers reaching deep strata was added to distribute loads vertically. Each pier supports about 500 tons with 11 to 16 piers per mat, offering over 5,500 tons of additional support. In total, the foundation system supports about 8,800 tons. Above this rests the mega columns, each weighing about 900 tons and bearing about 1,100 tons including truss loads. A total of 19 mega columns distributes and support the load of the trusses. Unlike typical stadiums that use circular columns for uniform compression and easy formwork, Mercedes-Benz Stadium employed rectangular mega columns for 2 key reasons. First, to precisely connect with straight trusses. Second, to visually integrate with the stadium's diamond-shaped geometry. Moreover, the flat surfaces allows for installation of the large LED screens. However, stress concentrations at corners pose the structure challenge, just by reinforcing vertical and bending rubber at the each edges. In this way, the foundation and mega columns ensured the structural stability of the Mercedes-Benz Stadium. Above them lies the truss system, which precisely controls the massive movements and load of the roof. Next, we will look into how this truss was designed and why it was a necessary choice. The roof truss and rail system weighed about 3,700 tons, with the moving roof 4,000 tons and scoreboard 1,000 tons. The 8 roof panels open like a camera aperture. This necessitated trusses, unlike arch truss used in bidirectional roofs. A lineal mega truss was chosen to support omnidirectional movements. The core challenge was combining stability and mobility using one structure. The solution was an octagonal fixed truss, a box-to-lead strategy. The structural frame for the roof is a massive octagonal fixed truss. This octagonal design, which is close to a circular shape but composed of straight members for efficient construction, was the optimal form to provide a stable framework for the entire roof structure. The box-to-lead strategy is a construction method that begins with building the central structure, the box, and then extends outward by constructing the leads, which consist of the 8 petal-shaped roof panels. The rigid octagonal truss acts as a box, supporting or guiding the movable leads known as panels. Each panel covers the box when closed, locking into a unified rigid roof surface. In conclusion, the octagonal fixed truss serves as a box, forming the foundation for ensuring the overall structural stability. This 27,000-ton, 224-meter truss required safe and precise site assembly. Thus, components were prefabricated into 30-meter segments at 15 off-site factories. Due to their size and weights, mega truss segments were lifted using North America's largest Manitowoc Model 31000 car crane and auxiliary cranes. Transporting such massive equipment into the Stadium Bowl involved disassembling components and reassembling them on-site via temporary access roads. Until stabilized, the trusses needed extensive temporary support. A Luma system with 60-meter high megashore towers provided the necessary strengths. The installation of the mega trusses was carried out symmetrically with structural stability as the top priority. Initially, the main sections of the primary trusses were lifted and installed first to ensure balance and stability of the overall structure. After the main truss sections were set in place, secondary trusses that interact and connect these primary elements were installed sequentially. Truss joints required high precision. Due to weld quality risks and field conditions, over 850,000 high-strength bolts were used. Field welding was limited to large closed sections. A decentering process with hydraulic jacks on megashore towers transferred the loads from temporary supports to the trusses. Afterward, temporary towers were removed and the truss system stood self-supporting. After the megatruss structure of the Mercedes-Benz Stadium was fully installed and self-supporting, the construction of the roof system immediately followed. This roof system is composed of pedal panels that move along rails mounted directly on the megatrusses, designed to operate as one continuous structural system with the truss. The first stage of the roof construction was the installation of the roof rails. Since the rails are directly fastened to the megatruss structure, the installation could proceed without additional temporary supports. Likewise, the pedal panels were aligned and fixed directly to the rails, allowing precise placement without any auxiliary supports. Once the rails were installed, pedal installation began. All components were prefabricated and pre-assembled on the stadium floor, including the bogie system. The key devices here are gravity bogies and uplift bogies. Each pedal weighs around 500 tons and is supported vertically by 8 gravity bogies. These are attached to steel brackets of the bottom of the pedal and sit directly on the top of the rail with double wheel sets. The wheels including guide fins to prevent lateral displacements and allow stable movement along the rails. Each gravity bogie can support approximately 600 kN, distributing loads evenly along the pedal's center of gravity and rail arc. However, since each pedal is cantilevered, its tip may sag or lift due to winds or interrupt. To counteract this, uplift bogies were also installed. These are fixed underneath the rails and connected using steel clamps and bolts from the bottom of the pedal with 6 uplift bogies per panel. Their wheels are pressed upward against the rails undersides to resist uplift and horizontal forces. Shim plates are used in conjunction to finally adjust clearance and prevent interference with the rail. Each pedal consists of 4 massive steel frames and weighs approximately 500 tons. To support this weight and enable smooth motion, precise coordination between the bogie system and rail was critical. Although the pedals appear to rotate around the center points, their motion is actually a combination of linear movements along straight rails following a near arc path. This design simplifies mechanical systems and enables natural opening closing without precise rotating shafts or complex things. But there's a question: why triangular and why 8 panels? The triangular is most geometrically efficient shape for fan-like rotation, minimizing interference between adjacent panels. The use of 8 panels divides 360 degrees evenly, supporting symmetrical loads distribution and structural balance. Although the panels appear to rotate around the center, they actually follow arc paths along radial rails. In a sense, it's not purely rotational movement but a combination of linear translation. Through this construction process, the retractable roof of Mercedes-Benz Stadium was completed. This was not merely an act of assembly but the result of precise structural analysis and advanced load control system and seamless coordination between prefabrication and on-site installation. Every structure and construction decision stemmed from a single architecture choice, our first 8-panel rotating roof. This roof wasn't an accessory, it was the origin point of the entire structure. The load path began at the roof, followed through the trusses and mega columns, and ended in the foundations. While the design moved from the top to the bottom, the construction rose from the bottom to the roof, forming an integration organic system. Unlike the Georgia Dome air-supported, maintenance-heavy design, Mercedes-Benz Stadium transformed the roof into an architectural icon and engineering challenge, redefining structure and construction from the top down. It's not merely a stadium built with new material or method. It's a structural answer showing how one design decision can reshape engineering, architecture, and construction as a whole.